Swayam Prabha. Digital India. Educated India.
Hello and welcome to the 17th session of our discussion on machining science. In our previous session, we discussed about the specific energy in grinding, and we said the specific energy in grinding is very high. In fact, it is an order of magnitude higher than in case of similar or comparable single point cutting tool or single point cutting machining, single point machining. Now, this is because that when the UC, when the T1 or the uncut thickness becomes less, the UC becomes very high, which we said to be as size effect. Now, why it happens is that during the grinding process or in grinding process, the T1 is normally very small, and within that small thickness, small layer, there is no imperfection or inhomogeneity, and the material behaves like an ideal material. So, in that case, the shear stress required to create the plastic deformation in the material becomes very high, and therefore, this power consumption becomes very high and the specific energy becomes very high. So, then we said that it is not only the size effect, but there are some other effects which occur in grinding, because of which the specific energy in grinding becomes very high. Let us see these phenomena. While size effect is an important factor contributing to high specific energy in grinding, now there is excessive rubbing and plowing during the grinding. They are also responsible along with the size effect for the increase in the or very high specific energy. During controlled force plunge grinding or during the cutting experiments with single abrasive grains, it has been found that under light loads there is no material removal and all the energy is consumed in rubbing. Let us explain through this curve. If we draw the radial depth of cut in the y axis and the normal force on wheel acting on the wheel in the x axis, then we will see that at the lower load, when the normal load or the normal force is still low, then there is almost no material removal. There is no material removal in fact, and the grinding wheel or the grains rub against the workpiece without removing the material. So, this zone is then termed as the rubbing zone, and here the power consumption is very high because it is rubbing and there is no material removal takes place. After that, after the increase in the normal force, further increase in the normal force, the radial depth of cut starts increasing. Therefore, the material is being removed, but not as much as it is in the cutting process. So, therefore, in this, because in this region there is more of plowing, and plowing, you understand that this material is not segregated completely, but this is plowed like we plow the land for cultivation. So, it is on the sides, okay, and the material is not really segregated from the workpiece. As the normal force further increases, then the material is segregated in terms of small chips and the cutting takes place. So, as you can understand that before the material removal actually takes place or before the cutting process actually takes place, there is plowing and there is rubbing, and because of the rubbing and plowing, lot of energy is spent without removal of material, and along with the size effect, this rubbing and plowing, these are also responsible for the higher specific consumption in the grinding process, as we said. Now, of course, the size effect is the main, that is the basic effect, followed by the rubbing and the plowing. Now, let us see the how grinding in the grinding process this can be plotted. For example, if we plot the same curve, this curve, if we plot in the log scale, let us say here it is a log of the uncut thickness and here it is the log of the specific energy. Then the curve will be a straight line like this, and this straight line can be represented by the equation as the u c t to the power m is equal to constant, or u c is proportional to inversely proportional to t to the power m. Here the m is constant, and this equation I wanted to show you, because then you will understand that what is the effect of this size effect in case of the grinding. For example, in case of the fine grinding range, the value of m is very high and it tends to close to 1. Okay. So, what does it mean? That in that case the layer is thickness is very small and there is no imperfection on that layer, and the size effect works. So, the specific energy becomes very high. And in case of rough grinding, where the T1 is still relatively higher, in that case we can have some imperfections, and along with the shear force which is applied, the imperfections move and the total shear force required will be less. So, the specific energy decreases. In that case, the value of m will be about 0.6. And to compare with this, for example, in case of single point cutting range, the value of exponent m will be about 0.2, because there are a lot of imperfections and the specific energy is less, because the shear stress required to remove the material or to create the plastic deformation, create the slip, is less. So, therefore, this indicates that the specific energy in turning process will be less than in case of, for example, fine grinding. Now, let us see how the grinding wheel wears out. If you plot the volume of wheel wear in the y axis, along the y axis, and the volume of work material removal along the x axis, you will find a curve of the wheel wear which will be more or less similar to the one that we have seen in case of the single point cutting tool. Initially, when the grinding wheel is comes in contact with the workpiece, grinding wheel surface has the sharp grains, they get very quickly dulled because of the rubbing, plowing, and because of the material removal from the workpiece. So, therefore, initially the wear is very high, and this zone is called the initial break in, like in case of the single point cutting tool. If you remember, we said that initially when the single point cutting tool comes in contact with the workpiece, because of the single point there is a very high stress concentration and it gets blunted very quickly. Same thing happens in case of the grinding wheel, that when the sharp grinding wheels with the sharp grains comes in contact with the workpiece, initially the wear is very high because those grains will be dulled. After that, as the work goes on, as the grinding process goes on, there is a very steady wear for a very long time. Okay. Because what happens is that when the grinding process goes on, there is a self sharpening phenomena. That means, when the grains will be worn out, they will be dislodged and the sharp grains will be coming which are behind the worn out grains, and always, almost always there will be sharp grains on the grinding wheel surface, particularly in case of the rough grinding. Okay. So, therefore, we say that this steady wear zone is very long, but after some time the wheel will be worn out so much that we need to have the reconditioning of the wheel. So, this is called the wheel dressing, when we take a diamond pin and with the help of a diamond pin we remove the outer layer of the grinding wheel. Okay. So, if you see the grinding wheel in this way, it is actually placed in along the centers. Okay. It is rotated, this is the grinding wheel, it is rotated, and then there is a diamond pin. This diamond pin goes to and fro to remove the outer layer, where we have either the because of the wheel glazing we have the worn out grains, or because of the wheel loading we have the chips embedded in the structure, that means in the voids between the grains, space between the grains. So, this is the process which is called the wheel dressing. and wheel dressing will be required when we have the wear goes very high and the worn out grains have to be removed or the chips embedded have to be removed, because the otherwise the specific energy will be very high and the power consumption will be very high. So, these are the phases which I have already said, that this is the rapid wear initially, then the steady wear, and the third phase is when the wheel dressing is necessary. Okay. Now, during the stock removal, I already told you this is the rough grinding such as vertical surface grinding, abrasive cutoff, etc. Phase 2 almost extends infinitely due to the fact that there is a continuous self sharpening action, and hence there is practically no wheel dulling, because behind the dull grains always there will be sharp grains and they will be revealing out, they will be coming out on the surface of the grinding wheel. Now, the wheel wear phenomena, it is like when the wheel gets in contact with the workpiece initially because of the wear, okay, because of the rubbing, because of the plowing. This is there is a flat created here, this is shown here A. So, the gradual wearing away of the sharpness of the cutting points resulting in the formation of wear flats on the grain tips. Okay. So, this is the due to the microfracture of cutting points, it could be due to plastic flow at the grain tips and due to crumbling of the sharp edges. These get aggravated due to high temperature obtained in the grinding. As we said earlier, that because of the very high speed of the grinding wheel, the temperature which is occurring in the grinding zone is very high. Then after that, if the forces are become higher, in that case the grain strength will not be able to withstand that force and grain can break along this BB, and this is called the fracture wear. Now, in case the grain is stronger than the bonding material and the bond is weaker, in that case the grain can be pulled out from the bond, and this is called the bond post fracture. That means, instead of the the grain breaking here, it can also be pulled up, the grain can be pulled out from the bond post, and there it is called the bond post fracture. Now, as you can see that if the grain fractures along the BB, then there will be sharp grains again, okay, because if the grain fractures out, this portion will have the sharp edges. So, therefore, this is also as we discussed in the case of the steady wear, the grain breaks and the sharp grains it will be considered as again a sharp grains, okay, because it is broken here, and you understand that the grain does not break along a straight line, it can break giving different edges, and those edges will be the sharp edges and they will take part in the material removal process. So, these are the three wear. First is the AA, which is called the attritious wear, BB is called the fracture wear, and CC is the bond post fracture. This is how the fracture in the grinding wheel takes place. Next topic that we will be discussing, followed by after the grinding process, is the oblique cutting. So, I would like to show you the diagrams which we have already seen earlier and compare the orthogonal cutting with the oblique cutting. So, we said that in case of orthogonal cutting, the tool edge is perfectly perpendicular to the direction of the cutting velocity vector. In case of oblique cutting, the tool is inclined at an angle, okay, and it does not make a 90-degree angle with the cutting velocity vector. So, therefore, we say that this cutting edge, let us say it is inclined with respect to the y axis by an angle of I, and earlier I mentioned that this angle is called the angle of obliquity or the tool inclination angle. Okay. Now, let us see that if we have the tool inclined, then what kind of forces are occurring with respect to the orthogonal cutting. Orthogonal cutting we have discussed while we have discussed the merchant circle diagram. These are the forces in oblique cutting. In the diagram it is shown. So, what is shown is that this is the tool in the base plane, let us say in one view, okay, and tool is inclined. Inclined means this tool edge is making an angle of I with respect to the line perpendicular to the cutting velocity vector. This is the cutting velocity vector. Okay. Now, this tool can be represented in a plane normal to this cutting edge, normal to the cutting edge as this. Okay. So, this is the rake face and this is the flank face of the tool, all right. And this can also be represented, these forces or this tool can also be represented in the shear plane as a shear plane. This is called the true view of the shear plane, meaning that if you look at the shear plane perpendicularly, see this is the true view, then you will see that what is the true view of the shear plane, and this is the true view of the rake plane. By true view we mean that this is the rake face. So, if you see look at the rake face exactly perpendicular to the rake face, you will see a view like this, which is called the true view. In oblique cutting, the resultant force R is not in the plane perpendicular to the finished surface as in case of the orthogonal cutting. It is convenient to consider 3 force components in the case of the oblique cutting, because the R resultant force is not in the plane perpendicular to the finished surface. So, these forces are parallel with the cutting velocity, which we will call as the Fc. Okay. Here by the way, this is written as the given as the Fp probably. If you can see that this is the Fp, this is we are calling equivalent what we have said as the Fc or the cutting force. So, this is the Fc cutting force. In this case I have written here in bracket that this is shown as the Fp, this is the cutting force. Another force is the perpendicular to the finished surface, this is Fq, here it is Fq. So, this Fq is perpendicular to the finished surface. This is shown here because this view is made perpendicular to the cutting plane, cutting edge here, okay, this plane. So, if you see this plane, for example, like this, okay, let us say this is AA, this is the view AA. So, I am not writing this as a sectional view because it is not sections, but for you to understand that if you take this section, the sectional view will be like this. In that case, of course, the tool will be hatched like this, but right now it is not hatched because it is not a sectional view, it is the view from the side. Okay. Third force component of the force is perpendicular to the perpendicular to cutting force and the this Fq, and this Fr is given here, this is the Fr. So, we have 3 forces Fc here or the Fp as it is shown here, Fr and Fq. Once again Fc or Fp, it is parallel to the cutting velocity vector which is here. This is perpendicular to the finished surface, and to both of them Fc or Fp and the Fq, the another force is the Fr. Okay, this is the Fr. So, this is the Fr. Fr is perpendicular to Fp as well as Fq, because Fq will be like this perpendicular to the finished surface. Now, to derive relations for the forces Fc, Fq and Fr in terms of stress on the shear plane, the following assumptions are made: that the tool tip is sharp, no rubbing or plowing forces act on the tool tip. Okay. Second thing is the stress distributions on the shear plane are uniform, and the resultant force R acting on the chip at the shear plane is equal, opposite and collinear to the force acting on the chip at the rake face. So, these 3 are the assumptions that have been taken for correlating Fc, Fq and Fr in terms of stress in the shear plane. Let us see how they can be correlated. We need to refer to this diagram. So, therefore, this diagram I have repeated on each of the slides. Now, as for orthogonal cutting, the resultant force can be considered to act as 2 components on the shear plane. So, we have the Fs Fn, that is along the shear plane and perpendicular to the shear plane, and two components on the rake face, F and N. F is parallel to the rake face and N is perpendicular to the rake face. So, this is like we have done that in case of the orthogonal cutting when we have discussed the merchant circle diagram. The shear force Fs is inclined at an angle nu s to the normal to the cutting edge in the shear plane. If you see the shear plane, that is the true view of the shear plane, what we are saying is that the Fs this is inclined to the cutting edge of the shear plane at an angle of the nu s, okay, to the normal to the cutting edge of the shear plane. So, let us say this is normal to the cutting edge of the shear plane, and to the normal this Fs is making an angle of nu s, that is what we said. Similarly, the friction force F is inclined at an angle nu c to the normal to the cutting edge. So, this is the let us say this is the normal to the cutting edge, okay, 90 degree, this is the cutting edge, this is the true view of the rake face, and to the normal to the cutting edge F, which is parallel to the rake face, is making an angle of nu c. Okay. Now, the resultant force therefore will be Fp square plus Fq square plus Fr square, because this is how we are taking the components of the resultant force, or we can have it as r prime square plus r2 prime square. If you can see that r prime square plus r2 prime square will be here, or let us say this will be Fp prime square plus Fq prime square plus Fr prime square. Now, we are saying that Fq and Fq prime will be the same, because this is acting at the plane normal to the cutting edge. So, therefore, Fq and the Fq prime they are the same. Okay. Fp and the Fr is making an angle of I with the Fp prime and Fr prime. So, therefore, Fp and the Fr is can be assumed to be equal to Fp prime and the Fr prime. If you see this, so what I mean to say is that Fr and the Fp, okay, they are both making an angle of I with this Fp prime and the Fr prime. So, therefore, Fp square plus Fq square plus Fr square can be written as Fp prime square. Fp prime is coming out to be in here. Okay. So, Fp prime is here, Fq square, Fq prime square, it is here, and the Fr prime square. Fr prime is making an angle of I with the Fr. Now, the direction of the shear force nu s is obtained from tan nu s is equal to Fr prime divided by Fs prime. So, tan nu s from here, if you can find out from this triangle, this will be Fr prime divided by Fs prime, which is equal to Fr prime is the F prime tan nu c. From this triangle you can find out, and Fs prime, like we said in the Merchant's diagram, that Fs, if you remember, was equal to r and the cos of phi plus lambda minus alpha. So, therefore, Fs prime, which is the that we have resolved the r prime into those 6 components like in the Merchant's diagram. Therefore, the Fs prime will be r prime into cos of phi n plus lambda n minus alpha n. So, I will remind you that Fs in case of Merchants we have written as r cos of phi plus lambda minus alpha. Okay. So, this is same here only with the normal plane. So, therefore, all these are in the normal, these angles are in the normal plane. This is the Fn, this is the lambda n, and this is the alpha n plus lambda n. So, you can find out these angles, and the tan nu s can be written as tan nu c sin lambda n divided by cos of phi n plus lambda n minus alpha n. The shear force Fs is on the shear plane is the K some constant, okay, that is the shear stress on the shear plane, and the AS is the area of the shear plane. So, area of the shear plane is BT divided by sine phi n plus cos I, and this is the shear stress on the shear plane. Earlier we represented that as a tau s. So, this is let us say equivalent to the K here what we are writing. So, this is the stress into area, and the area is this, stress is the K. Now, Fp can be expressed as Fp prime cos I plus Fr prime sin I. So, this you can find out from the from this curve or from this diagram. If you extend this view or extend this part. So, let us say at this the Fp is working is acting like that. Fp prime is making an angle of I with the Fp, okay, and Fr is making an angle of I with the Fr prime. Now, if you rearrange that, in that case Fp can be represented OA plus AB, okay, and the cos of I is equal to OA divided by Fp prime from here, and OA will be therefore Fp prime into cos I. Now, the sin I is AB by Fr prime from this triangle, okay. Hence, Fp will be equal to Fp prime cos I, this one, plus Fr prime sin I. This is what we have written here, that Fp can be written as Fp prime cos I, okay, which is OA, plus Fr prime sin I, which is AB, and OA plus AB can be assumed to be equal to this Fp. So, once it is this, in this case we can find out that the Fp prime is r prime cos of lambda n minus alpha n, okay. So, Fp prime we can find out from here. So, this is actually we have taken earlier also in case of the merchants. I will remind you that there we wrote Fc, which is actually this Fp, which is r cos of lambda minus alpha, is not it. This is orthogonal case, by the way. In orthogonal case, in merchants we have written that Fc is equal to r cos lambda minus alpha, you remember. So, Fp and Fc, this is here it is Fp. Now, the Fp prime is same r cos, but this is in the normal plane. So, therefore, lambda n minus alpha n, which can be written as Fs prime cos of lambda n minus alpha n divided by this, because r prime we have said as Fs prime divided by this, all right. Now, here it is written that Fs prime is equal to r prime into this. So, r prime equal to Fs prime divided by cos of phi n plus lambda n minus alpha n, and the Fr prime can be said to be equal to Fs into the sin nu s, that you can find out from this curve, from this diagram. So, the Fp can be said to be equal to Fs prime cos of this value plus Fs into this value, okay, because the Fp is actually the Fp prime cos I plus Fr prime sin I. Now, since Fs prime is Fs cos nu s from here, okay, Fp can be found out as Fs into this expression plus Fs sin of nu s into sin I. So, therefore, altogether what you can find out is that is the expression which we have taken that Fs common, and this expression will be the expression for the Fp. Now, the Fs, that is the shear force, this is equal to, we said earlier that the stress and the area of the shear plane, which is equal to Bt by sin phi n into cos I, which is the area, and K is the shear stress. So, therefore, Fp, this can be Fs can be replaced by this value, which is here, and then if you can simplify, this will give you the expression as follows. Okay. So, this is the expression for the Fp, which is the cutting force. Okay, this is cutting force, and this is equivalent to Fc in the case of the orthogonal cutting that we have discussed. So, now if we consider the orthogonal case, go back to the orthogonal case and find out how we have determined analytically the value of the Fc, you will find that there is a similarity, except that there are components which are coming in the normal plane. As we said, because only thing is that tool is inclined and the cutting forces are not anymore remaining in the x z plane, it will be in all x y z plane, and therefore, the R does not, resultant force does not remain perpendicular to the workpiece surface. Okay. As we said that initially, the R is not in the plane perpendicular to the finished surface. So, because of that, all this problem comes that all these components we have to take, and therefore, we have to find out the components separately, but there is a similarity between the oblique cutting and the orthogonal cutting, except the forces coming in the other planes, like the normal to the cutting edge, okay, and parallel to the cutting edge, like in other planes. Rest of the things we will discuss in our next session. Thank you for your attention.